welcome you to my recording today. Actually, you know, we started a topic some days ago about discussing tensions that can distinguish between prediction and explanation. I remember I mentioned five tensions that actually distinguish between the two. Of course, number one, I actually mentioned causation versus association. Intention number two, I mentioned theory versus data. Intention number three, I actually discussed what I call average and individual observation. So if you watch my video, or my previous videos, you're basically going to catch up with some of the things that we discuss. Okay. Today, I'm actually going to be discussing tension number 4, which is actually retrospective and prospective. I'm going to say that again. In today's video, I'm actually going to be discussing the tension number 4 that I call retrospective and prospective. Okay, before I go into that, I first want to appreciate those of you who actually send me messages, to ask questions. I basically want to believe that the responses that I provided, maybe you're satisfied with that, but if you're not satisfied with that, I need you to keep on sending messages. Okay, so I think I'm actually going to remind you of the major topic we are actually discussing. Initially I've been able to establish the fact that there's no there's a clear distinction between explaining and predicting. Initially it was actually taught by Ampere. I think I'm going to call that Ampere in 1948, where he equated model explanation to model prediction. Ampere tried to behave like some of my friends in economics or my friend in statistics that believe if their model can actually explain any phenomenon, the model should be able to predict. That was the thought of Ampere in 1948. But Emma and Resha in 1959, they realized that the uncertainty, in the two, the uncertainty he observed, the two of them observed in 1959 in model prediction and model explanation is not the same. And they actually concluded in their paper that the two cannot be equated. Of course, in 2001, Simon actually equates the distinction between the model prediction and the model explanation to be the same as the distinction between basic and applied science. In basic science, the basic science is actually aimed, at knowing the world. Knowing the world is more or less like we really want to understand the world and we want to explain the world. Of course, that is what we do in science in general. And that's why some scientists, they're going to say, okay, they don't care about prediction. In fact, some scientists actually accuse those that do prediction, as not being scientific. Okay. Because the science, they believe that science actually, what they pursue in the science, a cause a goal. What is the effect of what on what? You get what I mean? Okay, so they have their argument, but and why the applied science, the applied science is talking about how can we use the idea of the relationship among variables to basically make a prediction. You get what I mean? So it is tension that I'm actually going to discuss today will basically be on retrospective and prospective. But it's something I want to chip in for you to be able to understand before going to tension number 4. I want to have a recap, using notation. You realize that if you watch my previous videos where I discuss, each of those tensions, I didn't make reference to notations. And in statistical science, we pay more attention to notation. I'm actually going to use notation today. Let me say this: we find ourselves in a world where we basically um, want to understand the world, right? If possible, we also want to make prediction. But I want to believe before we can make a prediction about the way the world look, right? The way the world is going to look in the future, then we need to first understand what has been. And the reason why we are seeking for knowledge, because we need knowledge to be able to understand our stochastic environment. We live in a probability space. And let me just bust your bubble. The appearance of reality, appearance of the physical structure is independent of human knowledge. I'm going to say that again. Appearance of reality is independent of human knowledge. If I really want to understand the world, I need information, right? Information will translate into knowledge. You get what I mean? To be able to understand the world, we want to be secure, right? Okay. Now, um, we basically, the information we're looking for is not readily available. We need to collect data, right? And when we collect data, okay, using statistical procedure or the machine learning algorithm, will be able to get information that will translate into knowledge, and that will enable us to understand the world, to capture the world, to really have a way to make a prediction, from that. Now, the first tension I discussed in my previous video has to do with causation and association. Of course, I've already established the fact that, when you are pursuing a causal goal, when you are actually, um, you know, uh, dealing with a causation, then it means you are basically going to be explaining, which is what we do in statistics, which is what they do in economics, where they actually, they really want to understand the world. And from there, they're going to describe the world. Okay. And of course, association is correlation, where we basically want to make a prediction. Now, using notation now, we're actually going to have what we call X and Y. The Y is going to be response. We also call the outcome variable, right? Then we're going to have X. X can be a matrix, which could be combinations of features in machine learning, or independent variable or predictor variable in statistics. Okay, now we have Y, we got X, right? And let me say this. When we want to go by way of explanatory model, where we're actually pursuing a causal goal, okay, we need a particular function F. And that very function F represents an underlying causal function. Okay, in statistics, we normally specify that using the principle of subjectivism. When we specify our function, of course, we actually going to test hypotheses around that particular function. We believe that that function will relate, the set of independent variables to the outcome. Okay, so in other words, we believe, okay, the design matrix X is assumed to cause Y, which is the outcome, right? So that is for causation. And of course, we specify the model, with the model is basically going to have two major components. You're going to have the deterministic part, you're going to have the random part. And of course, all assumption would basically revolve around the random part, which we call the error. And that is the reason why in statistics, we basically go by way of investigating the behavior of a residual. But when you talk about predictive modeling, we actually believe F, that function F, captures the association of the relationship, between the X and Y. That's what we mean. Okay. The next tension I discussed was theory versus data. I remember the other time, it actually depends on the ingredient that you put into that, that we tell us whether we are doing the job of explanation or we're doing the job of prediction. I'm not saying that the difference between theory and data is the difference between explaining and predicting. That's not what I'm trying to say. But what I'm trying to say, when you actually focus more on the theory, you make your theory so heavy, right? And you basically use your data as a supplement or as as spices, then of course, you basically explain it. That's what we do in statistics, because the emphasis is more on the theory. Okay, we're basically going to test series of hypotheses, to actually, that will lead to the development of the causal theory. You get what I mean? Okay, so what I'm trying to talk about is the F. Okay, when you are doing, when you are pursuing what I call a causal goal, okay, where you're actually using explanatory model. Okay, the F is basically going to be constructed, in such a way that it will support, interpreting the estimated relationship between X and Y, and that will enable us, we're actually going to test, okay, the causal hypothesis based on that. So we're actually testing the causal hypothesis based on that particular function F. And that is the reason when we specify our model in statistics, we are guided by statistical theory. Okay, and of course, when you're guided by statistical theory, the mean function that we specify that relates the input with the output is basically what we're going to construct hypotheses on, and that we're going to test it on that. Okay, but let me tell you this. I said when you have a theory versus data, when you make your data, okay, to be more heavier than the theory, okay, where you basically use the theory in a less formal way, of course, you're actually pursuing a predictive goal. Okay, and of course, you're basically going to be using predictive model. Okay, and F, the function F is now being, constructed from the data. Let me tell you this: statistician, we don't actually, figure out our function, the functional form from the data, because we specify the functional form at the beginning. But the machine learning experts will use algorithm to figure out that particular functional form. So which means that very F will be computed from the data. You see the difference now, right? Between the theory and the data. Okay. I remember I talked about the average observations and, with an individual. Of course, in my last video, I actually said, in statistics, when you are pursuing a causal goal, we normally we have interest on average, average treatment or average treatment effect, average this, average that. Even when you actually put your regression model in place, whether linear or non-linear, you basically, when you want to interpret, okay, slope associated with the, with the any of the predator, you're basically going to measure average. But when you are talking about prediction, Of course, we actually use individual observation. So which means when you're talking about for statisticians or those who actually pursue causal goal, okay, they actually link causality to group. Okay, they link causality to group. Okay, why for prediction, we that is actually linked to individual level. You get what I mean? And I remember, I submitted in my last video that is there a way we can also link your causality to individual level and at the same time, base our prediction on a group level. I think that is basically going to be gainful. Okay, that is what we need. Okay, things are changing in the world. That is what is going to be gainful in the scientific world. Okay, now going into today's session, I basically want to talk about retrospective and prospective. Now, let me tell you this: when you are pursuing a causal goal, where you basically want to understand the world, okay, for you to be able to describe the world, we normally go retrospective. Going retrospective is more or less like we're collecting, data based on what has happened in the past. Okay, now, and that is the reason why in statistics, uh, we basically use the whole data set. We don't split our data set. Okay, we don't split our data set because we only want to explain, okay, not prediction. Because if you really want to understand what has happened, like you really want to gain insight into the world, for you to be able to, describe the world, you need the whole set of data because we are guided by last sample theory. Okay, we shouldn't forget about the central limit theorem. We shouldn't forget about asymptotic normality in statistics. So, but if you want to do prediction, if you want to predict, if you're pursuing a predictive goal, we normally go forward. We go prospective. Because of that, I'm actually going to say, predictive modeling is, forward looking. We're looking forward. Okay. And the F that I talked about the other time is actually constructed, for predicting new observation. We don't want to dwell too much to the past. You get what I mean? We don't want to dwell too much to the past. We basically, and that is why, machine learning expert does not really care about whether assumption hold or not. Okay, it's basically going to use all available data. It's targeting, future. It's targeting. It's going prospective. So, which means, the algorithm that is basically going to design, okay, we actually be done forward. The evaluation of the performance of the algorithm will basically going to be done forward. And that is the reason why when you are pursuing predictive goal, what we always do, we split our data, right? We split our data into two. We are the largest percentage of the data will be committed to training, and the other one will be committed to testing. The model, the algorithm, we actually learn the function, okay, from the training data, and of course, the model learn we actually be evaluated using the text data. Take a look at that. I remember the other time, actually said that you know uh, traditionally we split data into two, but right now we there been a kind of call that we should uh, you know partition that into three, where the first set is going to be training, the second set is going to be validating, and the third one is going to be testing. And actually they equate that to just like I'm teaching a class, right? The teaching will basically be training, right? When I give like a practice question, like practice test or practice exam, that will be validating because I actually want to see, I really want to figure out whether the student are getting the information I pass across. And of course, the final stage of the splitting we basically be testing. That is where the real exam comes up. Okay, in the machine learning world, they really focus more on the real exam. You get what I mean? So, which means they're looking forward, right? Okay, and that is why the perspective, comes up. Okay, so I'm actually, in summary, I'm gonna say, predictive modeling is forward-looking, and the function F is constructed, for predicting new observation. I think I told you how the function F is being constructed using the algorithm. The algorithm is basically going to learn that particular function, from your data. Okay, which means you're going to have a predicted function. We have a way to validate which particular, model work. Okay, but in contrary to what we do in statistics, or those who actually pursue causal goal, okay, they use explanatory modeling, and the explanatory modeling is actually retrospective. And of course, if it is retrospective, the function F that I talk about will actually be used to test some, set of hypotheses that you've put aside. And that is the reason why when we are trying to characterize relationship between variables, of course, we specified our function in statistics, and we actually going to place assumption on the error. Okay, that's why you have the assumptions of linearity, normality, constant variance, independence, absence of outlier, the high leverage, and the like. And of course, after that, we test a lot of hypotheses, okay, based on that particular functional form. You can now see the difference between explaining and predicting. Okay, this is where I'm actually going to stop today. And of course, the last tension that I'm actually going to talk about is going to be bias and variance. Okay, that will be the last tension I'm going to talk about in my next video. Of course, I basically need you to send me a message in case you, basically, you want to ask, question, 1 or 2 questions. Of course, I'm actually, going to reply you accordingly. I want to use this opportunity to appreciate those that will be